2008. So that's the first time we took a selfie of our own planet based from. So it's 1,000-fold. So the degree of difficulty increases when you go away from Earth. And so you go another 1,000 times. It's 250 million miles, right? So on the left side, you see from Mars, the Earth is like a little dot. And from Earth, we can see Mars also with the naked eye, red planet, and so that's the size of it, right? So this gives you a perspective. So go back some more. Okay, so the entire solar system, our planet is a little bit of bubble going around the sun, right? So go back, pull yourself further away. Okay? So the entire Milky Way galaxy, whatever the entire solar system is a little dot. Okay, so you see the sun. So the entire solar system is a little dot in the big Milky Way. So in terms of distance, so when you say, like for example, 15,000 light years, just to give you a perspective, if you are born 15,000 years ago and you turn on a light from Earth, it takes 15,000 years to go to the distance. So that gives you a dimension in terms of the distance, okay, how much our galaxy is, how big is our galaxy, right? So one light year is approximately 7 years. And this is a picture of taken from Earth about our Milky Way galaxy. This is an overlap picture. One at the top is taken from Lebanon, and one is taken from the Chile. You get a view of your galaxy from Earth. And this particular mission is a Hubble Telescope mission. You see the background. I like this picture. Okay, so you see a Hubble telescope there, and you see hundreds of galaxies behind them. So this picture was taken just by opening a little slit in the Hubble telescope. You take a view. So that is what you see in the. This is hundreds of galaxies, right? Open the window of the Hubble telescope a little more. And then again, like all these crew members, okay, you can see all sizes here, right? So, and with all multiple challenges, okay, some of them are pilots, some of them are astronomers, some of them are engineers, some of them are scientists. Okay, so you get a whole spectrum. This is the telescope. Just to give you a perspective, and we will be launching it this year. Hopefully, it will be successful. So the one hexagon, what you see in this is a mirror, is basically present in Hubble telescope. So imagine the magnitude of this telescope. Okay, the collection efficiency of this telescope. This telescope, we are planning to place it 1 million miles away from Earth, so in a Lagrangian point. The Lagrangian point is a place where, like our planetary bodies, like have a gravitational pull, and in that location, the Lagrangian point, if you leave an object, it will stay there for a long, long time. So it won't. So you don't have to basically. So this is a picture taken from Hubble telescope, right? The window is open, and you see thousands of galaxies. Okay. That gives you perspective. Okay, your galaxy is one of the smallest, and your sun is a dot, and Earth is even a smaller galaxy. So that's how I wanted to give you an idea, like we are a very small little dot in the big universe. This recently, like there was a lot of excitement about Perseverance landing on Mars site. So I wanted to give you a flavor about this Mars. So we have landed successfully. Many rovers before, ranging from Viking, Pathfinder, Opportunity, Spirit. Now this Perseverance, we landed on this desert crater. Okay, so this gives you perspective about which location this rover was landed, right? So that desert crater is this is about 40-kilometer thing, like a crater, and in that the landing site was a circle. Okay, so it's all well known now. perseverances right there. So Perseverance landed right in this location between these two dots and right here. That is where it's located. Why this particular site was selected? This looks like a river coming into a lake, and you see lots of delta. Okay? So if you term, in terms of if you're looking for any life in this particular planet, uh, long time ago, meaning 1 billion years or 5 billion years ago, then these are potential places you can look for. Basically, whether it's a microbe of some kind, or is it like any other, even the rock formation. Okay, you have an idea whether water was present in this location. So this gives you an idea of if water was there like 5 billion years ago, Mars has an atmosphere, right? Carbon dioxide, 95% carbon dioxide atmosphere. So it was there long time ago, but now it is not there. So you try to get an understanding what happened, right? So you cannot go to Venus, you cannot go to Mercury because they're all very hostile environment. Okay? Very high temperature, very high pressure, and very acidic environment. This is the closest you can go place where you can go and try to understand what was the word past, potential past. This is a very famous picture of the selfie, like where Perseverance was landing on Mars. Now you have Atrophy, Perseverance on the surface of the Mars. So, just to give you a flavor, like some of you maybe might have known this one. When our planet and Mars are close proximity, it takes about 6 months to go, and then they separate. So to come back to this configuration, and you have to wait for 1.5 years. So 1.5 years you can go around the Mars, and then take a trip back to Earth, and that will take another 6 months. Or you can land on Mars, spend this 1.5 years, okay, and then come back. Landing on any other planetary system is harder, and then coming back is even harder. Okay? So if you think about it, 6 months to go, perfect timing. If you miss the timing, you have to wait for another 2 years. Okay? Um, so launching date is very important. Okay? So you can have some flexibility and not too much. Then you have to stay there for 4.5 years, then come back another 6 months, right? So it's about 2.5 years. If your launch date there are some issues, then you have a buffer of 6 months. So the entire mission you have to plan for 3 years. So landing a rover is easier than taking a human being to another planet because you have to take all your whether it's oxygen, water, all food, and these are the essentials, right? So all these things you have to reposition because you don't have the bigger rocket to take everything at the time for 3 days. So for a human Mars mission, we will have two basically like mission just to reposition all these assets and establish it, and then humans can go. Why Mars? So I gave you a flavor because this is a place kind of like it has seasons, it has atmosphere, so you have protection from radiation, and then potentially it may have water, and it has carbon dioxide, so you can get actually oxygen from there. So if you minimize the luggage what you need to carry for the entire mission, you are better off, right? So living off of Earth, I mean like that wherever you land is an important. Then it has also Earth's gravity. It has two moons. So gravity is an important component. I'll give you some flavor of why that is important. Because our entire human race is basically evolved in one gravity. Okay, all your biology. So if you put you in the microgravity, and you lose a lot of these components, and we have associated with it. That's the reason why gravity also matters. Just to give you an idea, like what does it take to go, or like humans to go to Mars? On the left side is your input. The red is essential. water. Then rest of them are all the black ones are all basically like it's a luxury. Okay, taking a shower, washing your clothes, okay, all this luxury. So if you take all these things, about it will be 5 kilograms per person per day. You have to plan for 3 years, and you cannot throw away whatever you take, right? So whatever you drink, okay, so you need to recycling is an important component. So water regeneration is important, and you're going to live in a closed system because you cannot just walk on Mars. Okay, so you need to have a suit or you need to have a habitat, right? So air revitalization is important. Okay? And you need to have an environmental sensors, okay, all the chemicals that's generated there. Then microbes you need to worry about. So those are the resources you need to recycle and what it takes for human to live in an hostile, closed environment. So carbon dioxide is one of your output, right? But it's very toxic if the concentration goes up. So removing carbon dioxide is one of the essential things. So all your urine, okay, you need to recycle. So the technologies associated with all these things, okay, it has to be well proven and it should be redundant and reliability should be extremely high. If something goes wrong, party goes wrong, okay, or you cannot recycle your water, you didn't take enough water and you're dead in the water. So that is the reason why basically we test all these systems in a space environment. For example, um, it will be currently we are doing it for the past 20 years in space station, and we will be trying when we land on the lunar system maybe in 2024, 2025. So all these systems we will try to basically test them out. That is an important component. I told you about the recycling of water. So these four crew members and space station, what they're saying is like today's my coffee today is basically coffee of yesterday from all the crew members. Okay, in other words, the urine from all the crew members are basically recycled, and that is today's coffee. Okay, so that's what the scientists. The carbon dioxide removal, there are a lot of technologies in there, and from Apollo onwards, like lithium hydroxide is still used in many systems. What they call cans, and zeolite is another one, and amine bed is another one, anchored amine bed is another one, and Sabatier reaction. Okay, so there's another one. So from CO2, you can make oxygen also, and for CO2, issue is basically the concentration goes up, fatigue, okay, difficulty concentrating, irritability, and also headache. If the concentration is really high, you will die. So if you have watched Apollo 13 movie, so you might have seen the importance of carbon dioxide purification. And the lyo canisters they could not use. I mean, like because the design was basically like two different designs in other modules, so they cannot reuse those canisters basically. And if they were to be there for another day, they will be dead. So that's very important. And show you some of the fun pictures. Okay, so this is about when you're in microgravity. Okay, so you can do all these kinds of things. And your hairdo is harder. Party is very important because this is a system where your liquid component is separated and the solid is separated in this party. As an engineer, okay, these are all subsystems. Okay, and subsystems when it has to work in microgravity, and you have to take extra care in designing them. Basically, I'm going to use this as in one of the systems when you make a system for space missions, especially for a human space mission, right? So it has to work in a microgravity. So the solid is basically you have a suction, okay, so that will separate the solid and then compress and then process. The liquid is very precious, okay, so because you need to recycle, okay, and so all your systems should work. All the crew members should be able to basically maintain this toilet also. One toilet goes out, you're in deep trouble because you cannot carry diapers that much, okay, to survive the rest of your 3 years. So this is important. Food. Food is a very important component because it's a psychological of this thing, okay, as well as nutrition and nourishment, and because then you have to survive. Food is like, especially for dinner, like in all your manned ISS missions, they eat the dinner together. So that's one team. So stress reliever, social thing, and nourishment too. And here, like he has his entire dinner on his this thing basically on his lap because it's all Velcro. You cannot take salt and pepper just like that because it will fly away. So it has to be in the water medium. Chapati is the favorite one. Here they call takia. So you can put anything you want on this chapati and roll it up, and your taste buds are not the same as when you're in microgravity. So typically they put a hot sauce quite a bit on top of this one. Here they call sriracha sauce, and then they eat. Okay, so that is how the food system is right there. Yeah, here we see our Indian astronaut. Okay, so she's enjoying her dinner. Here is Scott Kelly, who stayed in space for 1 year. He has a record. And when we send cargo vehicles, we send the fresh fruits. Okay, so he's having fun with this. Look at this thing, right? This module. So you don't, not like what you can have only things in the ground, right? You can have in all dimensions. So all your hardware can be all over the place. Okay, so you can sleep anywhere you want to. And we have currently about 150 items, food items that to choose from. So before they go to space, we give them a 7-day menu they get to pick, and then we pre-position all this food before they fly. And imagine, like if you're going to Mars, these 155 items will not survive for 5 years because we have to pre-position your food, right? So that research is a very important component. So in terms of food technology, preservation, like you remove oxygen and remove water, that is the fundamental thing to preserve food for a long time. Then we freeze them too. Okay, so for those, that's the thing, like you have the rehydratable foods basically, is no water, no oxygen, and then the nitrogen is up there. So to uh, keep the food for a long time. Out of the 150 items, we have figured out at least 15 items are good for Mars missions so far. This is even no gravity, so you can lift anything you want and can fly. This is how you sleep. So you can sleep anywhere you want. Okay, so top or bottom. Watch the posture. So this is like a baby in mother's womb kind of, right? So that is your normal posture, like you get. Okay, so and for the head not to wobble, and they put a band-aid, and you can fly away. That's the reason why they have the approach. Air quality monitoring, like so we have an air quality monitor. This is the one in space station right now. We can measure many compounds, but these are the 20 things we worry about for the toxicity. I'm going to give you some flavor about human health, right? So you, as an engineering, aerospace engineering students, you learn a lot about a rocketry, right? But when you send a human, we treat this human as one of the subsystems. Human has a lot of baggage, right? So-called baggage. For humans in space missions, these are the primary hazards we identify. Radiation is one of them. Isolation, right? You all know, right, what isolation means, right? In the quarantine period, in the pandemic thing, right? So you want to get out of the house, right? You want to do things. So imagine you are in a 2-bedroom house room with 4 people in there for 3 years. You have to live with. So not kick them out, okay? And you may have different opinions, okay? And especially when you have issues about the spacecraft or living conditions, okay, which you cannot find a solution set, okay, and you go crazy. Okay? So the distance from the Earth, communication part of it, right? If you're in that far, it's about 20 minutes communication one way. So you cannot get any help from your mission control from Earth. So you have to manage. Okay, so autonomous is another key component for it, right? So then gravity is changed, right? So the 6 months travel to Mars is a microgravity. Once you land, it is 2/3 gravity. Then you have microgravity. So when you put humans in microgravity, things change in your system as a human system. Then the environment, I told you about the carbon dioxide and others, right? So because of this, in the human system, you have lots of risk. So when there is no load on your bone in the microgravity conditions, you have bone loss. Okay, so approximately 1%, 1.5% per month. So your bone can be brittle, right? So you need to have countermeasures to offset this bone loss. And the muscle, you don't need any use your muscle at all because it's no gravity there, right? So you have muscle atrophy, right? Imagine you're in the bed for 6 months and try to get down, then you will have an idea, okay, what does it mean muscle atrophy is, right? So then balance disorder, right? You take it for granted just walking, right, picking up things, and you to do that you need three systems basically. You need feedback from your feet, eyes telling you like what is up and down, and your ear like the hair cells tell you like whether about your posture. So if you're falling down, and all these three things work together to come back. So in microgravity, all these things are lost. Okay, so basically you don't have orientation at all. Okay, your system is basically completely messed up. So, but when you land on Mars, that gravity will kick in. When you land on Earth, that will kick in. So that is a big deal, basically. And you will not be able to walk, and for at least a few days, and then you will have other issues too, what we call neurovestibular issues, and radiation and other issues. So behavioral health is another important this thing issue. If something goes wrong, you can select a perfect team for 4 people to live there for 3 years. But if things are not together, and it'll be the behavioral health issue of an individual and as a team is a very big issue. So for the past 15 years, I worry about like getting a standards for all these things, how to do this, how to prevent them, all the technologies associated with this, what kind of treatment we do. So those are the things I spent past 15 years. So this gives you a summary, like I said, the radiation issue, like what happens, like a long time you can get a cancer, like there's a distance I told you, you cannot, whatever the medical kit you have, that's what you need to live with. You cannot have a surgery because you don't have a capability. Environment, you need to have all the hardware necessary to keep your environment under check. Isolation and confinement. How do you take care of yourself with the behavioral part? We underestimate mental health issues in Earth, but this gets basically like multiplied many fold when you're in a faraway distance and there is a conflict, and you have to pay a lot more importance to this mental health things, which you might have seen like during this pandemic period too. Then altered gravity, so it has a balance disorders. And all your fluid basically goes up to your head, okay? And associated with that, we have some issues too. Talking about radiation, right? So the radiation is basically you have two kinds of radiation. One can come from sun, another one from galactic cosmic radiation from the universe actually. So I showed you a picture of the universe, right? So our sun is basically two hydrogen atoms in a fusion, you get helium, right? And then fusion energy is the one what you get in terms of light, heat, and everything else, right? And so this is a spotless sun. Okay, you will get a sunspot in the sun, and that will give you basically big ejection of this thing, coronal mass ejection, right? So you get this particles coming from the sun. So this is a perfect no spot sun. This video gives you a little glimpse of basically how this ejection can come from. So the primary particles involved are hydrogen atoms, helium, protons. Okay, all these particles with a high energy will be coming ejected into the atmosphere. So if our Earth is in that line of sight, or if you're traveling from Earth to Mars, you're in the line of sight, you will be affected. So okay, this can be very massive too, like a solar flare can be massive. Just to give you an idea of the size of the solar flare. Okay, so this is a Earth in comparison to a very small solar flare from the sun. Okay, so if this solar flare comes to Earth and it can swallow the entire Earth. You see this arc thing, basically you have a powerful magnetic field in the sun also. So it tries to pull this particle back again. That's why you see some of them coming out and some of them is basically coming back into the sun as a loop. How we are protected? Our geomagnetic field is our protection. Okay, so if this one, the sun solar flare comes in, this geomagnetic field pushes these particles outside this Earth, right? So this is like a little magnet. And so this little spherical magnet, you have a hole on the top and hole at the bottom. Okay, so there is not much of a protection. So these particles can come through this channel from the top in the polar region, and so that is responsible for the aurora lights, whatever you see in the North Pole. If you see the aurora from the space station, and this is the kind of a view you get, right? So. And Jupiter has an aurora too. So it's a beautiful picture of the aurora. Saturn has an aurora too. So how does this one work? The solar cycles. Okay, so if you plot the number of sunspots like per day, you get 11-year cycle. So we are, as a human race, we track this for the past 290 years or so. So this is a 25th cycle. Literally, we are paying attention to. Okay, so meaning if the number of sunspots goes up and the probability of the solar flare increases, so we have to be very careful about it. So this is the cycle, and so these are the particles when you're coming to Earth. If you study mass spectrometry, like the depending on the charge and the mass of the particle, these particles will align in different locations. Basically, so those are the proton and high energy particles lined up here around the Earth. This is what we call it as a Van Allen belt. So we are protected like a cocoon by this geomagnetic field, right? So whenever we go past this Van Allen belt, then you lose this so-called protection. So you need to be aware of these particles, okay, outside there. So whatever I told you about sun is only a small set of particles. The galactic cosmic radiation is a lot more dangerous because these particles are like iron, silicon, carbon, oxygen, all nuclear. Okay, imagine these high charged particles coming. It'll go from your body from one end to another end, basically, without any issues. Okay, so protecting these particles are harder. So how do we get these particles? Okay, see the sun, I told you, like two hydrogen gives helium, but we have suns which has different set of for this fusion energy, two carbon combining together, okay, so to another one. So those are the suns coming from different galaxies in the universe, ejecting those particles constantly. So that is what you're getting as a galactic cosmic radiation. This is about the bone glass part of it. Okay, so if you take this one, if it's a space flight, it's a continuous line, right? And you have no protection, for example, no exercise, no active exercise, and no medication. So that's the rate. But the postmenopausal women part of it, right? So that's your dotted line, right? So in 2 years, okay, that's the rate of your bone loss, okay, for that. So that gives you an idea the accelerated state. And then we have some exercises. We have treadmill, we have weightlifting machines, and then we have cyclic ergometer. So when you do this exercise, this bone loss basically decreases. So we have an idea. And so this is a bicycle we have. You're going to have a seat for this bicycle. And this is a weightlifting machine. Okay, as an engineer, okay, when you're designing a system like this, imagine you're in a microgravity. Any force you put it on the system, it will have a counter force, right? So the entire vehicle can go crazy. Okay, so you need to have basically you need to offset that part. Okay, so that is also an integral part of it. Not only a weightlifting machine. Okay, but you need to have that counterbalance in the system. Otherwise, your spacecraft, in this case, this is a space station, can go out of orbit quickly. Okay, the same thing with the treadmill also. So you may be wondering, like, how can you have a weightlifting machine in an microgravity, weightless environment? Okay, think about it. So here, like Sunita, or Sunny, she is running on a treadmill, but she's tethered. Okay, otherwise, she'll float away because then she will not be able to put her entire load on her muscle and bone. That is important, right, for the preserving muscle and bone loss, right? So she's a good marathon runner, and she's a helicopter pilot also. She's a commander for one of the future Boeing missions. Okay? She's an outstanding person. So you see that all of them are anchored, okay? And we monitor the like the ground forces and everything else. So the system is very comprehensive, and we have a good feedback. So the vibration isolation system, as an engineer, is part of it. Okay? If this system weighs about 200 pounds, right? That system may be like 300 pounds. So launching every ounce pound is an important thing for space. Fluid shift, right? So left is Peggy Wilson, like she's a scientist from our lab. She used to be before becoming an astronaut. And when she was in space, like we get a puffy face basically because the fluid basically on. Because of this, we have some eye-related issues. We're trying to understand, so hopefully we'll find some solutions. So we have some monitors. This is a fundoscope in space station to take the picture of the retina. And we have some understanding like who gets it and who doesn't. Because all of them don't get this eye issues. Okay? And biochemistry, if you have studied at some point, homocysteine is basically one of the components, the higher concentration for the people who are susceptible for this vision issues. And if you have studied the Krebs cycle, okay, as an engineer, like you guys do, like feedback control mechanism, right? So here, like homocysteine is one of these control systems, right? If this is too high and there are other things you need to compensate. In biology terms, like a B complex is the one, like you see this B6, the one B12 biochain. So if you give that, increase this concentration, and we can balance this homocysteine and potentially reducing this IH-related issue. I told you about this thing, like your stress level can go up, right? So this is a picture, like you might have realized in day-to-day life, like if you're 50 and women, above, women especially get this things, right? What they call chickenpox, right? So if your immunity level goes down, these viruses are all basically embedded in your body. Okay, so that will come back. Okay, and that is what you see as the chickenpox. So this data set tells you, like before flight, these viruses from your saliva is very low, but during the flight that goes up significantly higher. Okay, and we have not reached the point of chickenpox is about 10,000 counts. We get about 1,000 to 1,200 counts, and you get a chickenpox when you are older. Okay, and you know the pain. Okay, it's miserable. And so this is another cortisol also is another indicator to monitor the crew member stress level. Okay, so that is an important quantity. How do you quantify stress level in your system, right? And in this pandemic scenario, right, people with lower immunity get the higher tendency to get the virus. This immunity reduction can be due to many underlying conditions, diabetes, okay, or it could be heart conditions, and so they have the highest susceptibility. Even the stress level, this is an indication, right? Another population is first year medical students, they call it. Okay, so their level is also quite high. And your physics changes completely. Okay, so this is a flame like in the ground, and this is a flame in microgravity, right? So how do you have imagine your rocket system and you're building it, okay? And how the thing dissipates, right? All those things play a role, and how the fuel efficiency could be potentially increased if the flame is of this kind. How can you have microgravity in one gravity Earth? Okay, so this is the Vomit Comet picture. So basically, you take the aircraft 45-degree angle, okay, about 35,000 feet, and then come back down. So you get about 25 seconds of microgravity. So where these are all astronaut candidates, we call them ASCANs, and so they get to feel this microgravity for 25 seconds. This parabola, we repeat it for in a typical flight, maybe 25 to 40 times. So they get an idea what is microgravity in 25 seconds for 25 to 40 times. Okay. Some of the hardware we basically design will be tested in this microgravity kind of an environment before we take it to the actual flight also. So that gives us an idea. Space suit. This itself is like a spacecraft because all the system, you need to protect the humans and all the power systems, and it's all completely battery operated, and all of them are inherent in the system. For example, you need to remove your carbon dioxide, and you need to have a lighting conditions, because if you are in space, for example, space station, every 90 minutes you will have a sunrise. Okay, so you will have complete darkness. Okay? Typical our extravehicular activity is about 6 hours. So imagine within 6 hours you have multiple sunlights and sunsets. Okay? So you have an extreme heat load, and as well as no light at all. So you need to operate in those conditions. So this is a self-propelling thing, like a system. Basically, you're in microgravity. You don't need big propulsion system. A canister full of a compressed gas, you push it in one direction, so you can come back to your vehicle. Okay, so that's what this is about. So as an engineer, when you design this, okay, and you might have heard about Human System Standard 3001, where all the standards are written. And from the standards, when you build spacecraft or spacesuit, anything for that matter, and you will have a preliminary, you need to have all the stakeholders. Okay, that is very important. Okay, customer, maintenance people, all of them should be the stakeholders. Any hardware you design as an engineer, right? That is an important step. It can take as much time as you want to define your requirements. Then you do your preliminary design review. Then you do your critical design review. Then you make a hardware and test them out multiple times. If it is possible to test them in the actual conditions in which it should be tested, for example, microgravity, then we fly them in the spacecraft, right? So it has to be tested multiple times before you build the actual flight hardware. Okay. So I'll just stress again, okay, stakeholder input is very important. Testing and evaluation of this integrated system, because this system, for example, should have multiple subsystems. When you integrate all of them, you need to do an integrated testing and evaluation. That is very important. I want to stress again and again. In system engineering, they will teach you all this, okay, but some of the things we learned it in a hard way. Okay, so when you build systems for future, anything, whether it's iPhone, any device for the Earth or anything else, that is an important factor. Human factors is another important factor too. Okay, and don't expect humans are super beings basically, and you have human limitations. For example, okay, if I put a the suit, my reach to a certain location is limited. Okay, so when I don't have a suit, okay, I can reach certain distance, right? But it is restricted. That element is important. The view, okay, what I can see and what I cannot see, right? That is important. And always we use a buddy system. When something goes wrong, how do you take care of them? Okay. And recently we had one incident about the water flooding within the suit. Okay? If we have not brought them back into the station on time, it would have been dead. Okay. So each subsystem. So in that, when we do this thing like going back, what went wrong? Basically, the quality of the water they use inside the system of the suit is the culprit. So don't take anything for granted. Okay, pay attention to details all the way. Okay, so in the suit, for example, so this is the first garment, a cooling garment, because you're going outside the this thing like station. So the temperature swing is quite high. As I told you, like you have sunrise and sunset like every 90 minutes, right? So they you have a liquid cooling garment, and then they're holding up. So this is the space. Okay, in the future, you may be interested in knowing, like, there are some general questions, Professor Shang, like he sent me, why do we do this thing? Why do we have to spend all this money? Can we spend it to take care of human beings in Earth, right? Imagine 1905. Then think about 1950s, 2000, 2020. You can go to any part of this world, okay, whenever you want. How did this happen? Because of the spacecraft, right? I mean, because of the flight. So in the beginning, it is a harder thing, right? And then you learn, and then you have to take risks. Is death is part of it? Yes, of course. There are many accidents early on. So imagine a flight from 1930s to 1940s, because it's evolving, right? In the beginning, it was a mail carrier, right? And then people were flying. So this is the age where this rocket science will become as one of the transportation modes. It can happen in many other ways. So that's one of the reasons, like you have private investment as part of it. So this is the SpaceX Capsule, and the 4 crew members are flying. At the end of the year, SpaceX is having public for crew members. They call the mission Inspiration 4. And they are going to launch humans, basically, not astronauts, like I mean trained astronauts, just like any public event, right? So space flight in another 10 years. So now the cost may be like several $millions per ticket, and in another 10 to 15 years, this will be a routine thing. Okay? If you want to go to space and stay there for 3 days, I mean, just staying in another place, and you will see an appreciation for the value of the Earth as an entity. Okay, that's the only place we have right now, and so you will have a lot more insight and many other aspects, whether it is science, engineering, and so that is the directions in which it is going. So I told you about the Apollo mission 2024, and for about a few years to learn how all these systems work in this 1/6 gravity and the very harsh conditions. We will be planning to go to South Pole, and potentially there may be water underneath, so we can take water from there and then get hydrogen and oxygen, and you don't have to carry your fuel. That's a possibility. And in the Perseverance one of the hardware you might have seen is Moxie. Basically, like they generated oxygen from CO2, right? So these technologies can be proved there in these missions. Um, these missions are called Artemis program. Okay, so that's what it will be. So in Greek mythology, it's the princess of Apollo. Locations, there may be many interesting locations, but we will be going down to the South Pole. So that is the intention. Why South Pole? And even in South Pole, which location? These communication and lighting conditions are one of the key things, basically. For example, I think the Vikram landing is they happened in the South Pole too. And it is a very tough environment, no question. And thing with this, like all these works are done by very talented, dedicated engineers, scientists, physicians, and astronauts. All these tests, okay, and I need some knowledge. Grace make a difference. For all your efforts, passion is one of the things, and perseverance and patience is another component, is part of it. I don't know if this audio will work. It sound like it. If it doesn't work, I will tell you what Collins told us about a couple of years ago. He passed away this year. Kishan, let me know whether you hear.
Yes, sir, it is audible.
Oh, good. You see the astronaut on the right side, and she's one of the potential ones who may land on the moon. So it gives you a preview, okay? One of them. So this is Mike Collins. He came to our center to talk. On the left side is our center director, and so he came for the 50th anniversary of this Apollo 11. And so that is a question. Like when the mission control, when they asked, "Hey, what do you see?" He saw the entire world in his window. Okay, a lot of like only few of them in the whole humanity got to see that kind of perspective. So what he sees is fragility. So this is only place that's given to you, right? So he has entirely a different perspective when you see from the window, and what responsibility, what he says is all the time basically he has a burden on his shoulders. I cannot take care of it, whatever I do. So another element, see, after all these 50 years, now it's the human part of it, right? As a human in Earth, what is in your window? Okay, your spouse, your children, grandchildren, whoever, friends, and look at that in that window too. Okay, and that's also an important one. So that's an analogy we're trying to do basically. So this kid, cancer, so he passed away recently, and we were fortunate to see him in person, and then because he's a very reserved kind of a person, he's a pilot. So, but anyway, so with that, I want to stop my presentation, and I will get questions from you all. Okay, I'll shrink this window so I can see you all. Is it okay, Dr. Shan, so you can ask me questions?
Yes, sir. Sure, sir. It is a wonderful presentation, first of all. So thank you for your spending your time, sir. So there are a few questions from the audience. So let me ask you, like you can reply directly to them. If you are having any queries, the audience, if you are having any queries, you can type in the chat box. I will ask the question to sir. First question, sir, like one name from Yarrow Girl. She has asked about fusion energy. She has asked about fusion energy, how it is going to help for space studies.
Whether it will be useful.
Yeah, tell about fusion energy. She has asked.
Okay. Using fusion energy for future propulsion, it will be a harder thing because you need a minimum temperature, high temperature system, right? So in the Earth, we try to do that part with focusing on high energy lasers and all that to create fusion. And what I call harvesting the energy for this propulsion is harder. But fission related energy, for example, nuclear reactor, mini nuclear reactors. Okay, so that is possible, that is viable, actually. So that is doable, and it is scalable. You want a smaller one, you can have a smaller one. Take for example, Perseverance. As an example, the Perseverance, the energy is coming from a plutonium isotope in the system. Okay, it is not depending on solar energy anymore. Okay, from that energy, the heat energy is transferred into an electrical energy. So that's what it is running basically. Okay, so nuclear power, fission-related one is possible for the future propulsion. Fusion-related one is kind of a long way.
Okay. Okay, sir. Next one is should people be flown to space instead of robots? Like whether humans have to fly instead of robots, or we can send robots
Okay.
itself.
I have various perspectives. Okay, so humans are, you have intellect. Okay, whatever the robots you make, your intellect basically derived this thing, questions only you can ask or you can program only. So what I call this basically is a pre-orchestrated questions. Okay, those are the things you can see. I'll give you two examples. So any crew member, you ask them, hey, what is the biggest thing during this flight? As soon as I go and see the Earth, my entire perspective of the life changed within a fraction of a second. This is what the entire world is. and I'm going to live there for 100 years and that's it. What about all these borders? I don't see any borders. So then a robot taking a picture, okay, and you look at the picture is different from a human with an intellect looking at this, and all of us are gifted with different talents. One of you may look at this problem in a different way, or even the perspective you get is entirely different compared to all other human beings. Okay. Another question is about like why do we have to go to space? Okay. Why do you have to fly in an airplane? Okay, because it's possible. People in 1900 they could not do it, right? And imagine the technology progress you made along this way, right? So human, then the same token, right? So this is like when you go above the Earth, go to Mars, for example. So perseverance, geology, and all that other stuff. But when you see what you see is using your camera, okay, and then you program your Percy for the future explorations, whether it's a rock collections or whatever the case may be, right? If there is a human there, it'll be entirely different. So he will ask multiple questions. Why is it okay, and why this is not okay? And the number of questions you get, okay, even sitting in your class, right, and you listen to a lecture, and then you listen to a lecture in person, okay, that makes a big difference because your human mind is amazing, okay. So any new concept that is given to you, okay, one, you may not understand that much, so you have a curiosity to ask, what about this? What about that? Okay, and that human component is an essential one for a future growth. So that's my perspective.
Okay. Okay, sir. Fine. Another question from Cyan Mondal. Is it possible to wear the space suit continuously till we live in space, or it may affect the body?
For example, like if you're going to Mars, okay, or if you're going to Moon, for example, so you will have a habitat. So within the habitat, it's like just living in a one-bedroom apartment, right? So there's all like we will have a pressurized cabin. So in the future, we are thinking there are many other issues associated with that. I can talk to you because decompression sickness and all that we worry about. And so potentially, like it could be right now. It's okay. You're not in the SI system, so I'll tell you in pressure in um, the whole system, right? 14 psi is the pressure of one atmosphere, right? So we are thinking about 8 psi habitat, right? And 34% oxygen because you need higher oxygen if your pressure is low, right? For you to survive. So your habitat will be in the condition, okay? So if you want to step out, then you wear a suit. Otherwise, you don't have to wear a suit. Okay, so that is the current thing. Okay, so in the moon, the same way. If you don't have a habitat, you stay in your spacecraft. Okay, so your pressure and all these conditions are okay, and you can be in the seats. Okay, so in a short way. So that is how it will be.
Okay, sir. Hope it is the correct answer for him. The next question is like it is a common question like whether human race need to like we have to move to another planet, whether that is necessary right now or like it is not necessary.
At this point in time, I'll say not necessary. Okay, in 1,000 years, it's a different story. Can we make, for example, the closest one is Mars? Can we make it as a livable planet? It is doable. Okay, the technology what we have, it is doable. We can create an atmosphere like a livable atmosphere. It takes about, from our estimate, it will take 5,000 years. Okay, so that is the estimate. We can make the place livable, right? So whether it is necessary to move our human race into that thing, it is not financially viable, and technically also is not viable for a smaller number of people, not for a whole colony of human race.
The final question: should all governments prioritize spending on space exploration?
Let me give you one example because we are living in the pandemic, right?
Yes.
Um, You see this oxygen meter people were talking about? You put it in your finger, like as soon as you get in the hospital or whatever.
Yes,
That
sir.
was discovered during Apollo because the spacesuit is basically 100% oxygen. The vehicle was 100% oxygen. So you cannot have electrically based sensor. So they wanted a non-invasive oxygen sensor. So that is the optical sensor they device. This is one example. Okay, there are many, many, many examples. Okay. So it is this discovery is designed for a different purpose, but it's a second nature to us. Okay, everybody in the world talks about oxygen, just meter, right? Oxygen meter. In every household they talk about it, right? And so this is one example, and there are many, many examples.
Okay,
So
sir.
it's important for the governments to spend on this thing. But the thing is, like even when you go to Mars, okay, it's becoming very like very expensive. So if you collaborate, you're better off, okay, much better off. So all the future missions, from my point of view, it will be happening in an international basis and not as a single country. That's the thing. And you can see all these development basically. So you have a consortium in an international level. 24 countries basically agreed on what kind of this thing like expedition you can go as an international community to Moon, Mars, and future, like whether it's an asteroid. So all basically it's a collaborative environment. So even in this time and age, you will see the importance of collaboration at various levels: educational, technical, and healthcare. Healthcare system you might have seen, right? Like to the discovery, from discovery to manufacturing to implementation, and it's all international collaborative thing. The more we do, better off we become, basically. Even the vaccine, whatever you were seeing, right? That the rate at which they were able to develop this one and manufacture billions of doses, right? So that's one great example. And then sharing the data from one country to another country will save millions of people. Okay, so that's again a collaborative one. So you can talk about in healthcare, for example, privacy and all that other stuff, right? But when it is life and death, it matters. Collaborative effort matters. So as an engineers, I'm scientists, and educational community, like a collaboration is an important component. Okay, you are not, you cannot as an do it in one country, as a single country, like you will be wasting a lot of your energy and time.
Okay,
That's
sir.
my perspective.
Yeah. With this, we can end the session. First of all, I would like to thank you for your valuable time, because as a deputy chief in a particular biotechnology division, you have a lot of work and you have lot of priorities. So even in that time, you have spent an hour for the students community of from the country India. So thank you, sir. Thank you for that wonderful presentation, and sure that the students have gained much knowledge from your topic and presentation.
Yeah, thank you so much. Yeah, I was excited to share what I know with your community, so I'm very grateful for that. So,
Yes, sir.
thanks, Kishan, for your
Yes, sir.
support.
Thank you, sir. Thank you. Thank you very much. We can end the session, sir.
Okay, okay, all right. Can you follow? See what kind of process they are.